Hello and welcome to this Tech Talk, where you will learn about the Variable Conductance Thermal Management System being developed by Triton Systems. In this presentation, I will describe the technology, explain what sets it apart from existing solutions, and define the path toward commercialization. Triton Systems is a small business in Chelmsford, Massachusetts, with over 100 scientists and engineers and several state-of-the-art laboratories in a secret-level cleared facility. Triton has created over $2 billion in shareholder value over the past 15 years and earned the Tibbets Award in 2016 for successful development and transition of impactful technology. Triton has a strong track record of commercializing technologies derived from SBIR funding, including nickel-free conductive filler used on F-35 aircraft, pressure-sensitive adhesives used on F-22 aircraft, and microstructure biosensors for blood pressure monitoring, which led to a successful spin-off company. Triton is also involved in a joint venture to manufacture personal air mobility systems for warfighters. Triton's variable conductance system was developed to satisfy the Navy's need to control the temperature of thermally sensitive high-tech fielded sensors that are subject to rapidly changing ambient conditions. Existing solutions are commonly inefficient or power-intensive, especially when the difference in temperature between the sensor and its environment is large. Other solutions can be difficult to integrate into complex shapes and must be highly customized to their intended application. The specific performance objectives set forth by the Navy include maintaining the sensor within 5 degrees of 55 degrees Celsius, as environmental conditions vary from -10 to 40 degrees Celsius. The sensor will be 2.5 to 25 liters in volume and include an internal heat load between 1 and 50 watts. The variable conductance system must reject heat from both flat and curved surfaces, be less than 10% the volume of the sensor, and draw less than 1 watt of power. The operational use of Triton's variable conductance thermal management system will be for the low-power thermal stabilization of temperature-sensitive sensors. Existing technologies such as thermoelectrics and simple resistance heaters are inefficient or power-intensive, especially when the difference in temperature between the sensor and environment is large. Variable conductance heat pipes perform effectively, but can be difficult to integrate into devices, require highly customized configurations, and are difficult to integrate with complex surfaces. Triton's technology improves upon these alternatives by using a flexible composite foam thermal interface that can wrap around and conform to complex surfaces. The thermal conductance of the interface can be adjusted with very low power by compressing the foam structure. Heat transfer through the foam occurs passively. Triton's composite foam exhibits an 80-to-1 increased thermal conductance when compressed. It is used as a thermal interface between a device and its environment and integrated with low-power actuators and a thermal control system that adjusts foam's thickness. Technology is also capable of being paired with passive actuators, such as those that rely on thermal expansion to actuate. This timeline depicts our progress through Phase 1 and Phase 2 programs, along with our path forward towards commercialization and transition. During Phase 1, we demonstrated conductance turndown using composite foam and piezoelectric actuators and began manufacturing the variable conductance foam in our labs. During Phase 2, we integrated the technology into a mock sensor that was developed to replicate a real-world application. We tested and demonstrated the technology in this application. Going forward in Phase 2, we plan to repeat our findings with additional shapes, sizes, and configurations of the mock sensor. In a proposed Phase 2 option, Triton will develop an additional demonstration sensor more representative of real-world applications, and demonstrate the variable conductance technology with this sensor. Beyond Phase 2, Triton plans to move beyond these mock sensors and fit the variable conductance system into a real-world sensor. To advance the technology to market, Triton is looking to identify a candidate sensor, adapt the design to integrate with this sensor, and demonstrate its effectiveness in a real or simulated environment. The Navy's Strategic Systems Program is Triton's primary transition advocate. Triton is seeking collaboration with sensor developers to better understand the thermal management requirements for their sensors and better understand their performance needs and integration constraints. The end goal for Triton is to license the technology to a sensor OEM, or system integrator. If you're interested in learning more about Triton's variable conductance thermal management technology, contact Matt Davis at the contact information listed on this slide. Thank you for your time.